All right. And so, yeah, so we're going to continue on with section 38, which technically this part is not in the curriculum, but I think it's important to kind of see like other clustering algorithms like DBSCAN, or especially you can detect things like outliers and stuff. So remind me, we haven't gone through, like I might have mentioned it, but we haven't like really gone through it at all for DBSCAN. Is that right? Okay, good. I see some head shakes. So, okay, that's what I thought, but I just wanted to make sure. Okay, so let me go ahead and start sharing my screen. And this should now be up as well on the repo on GitHub too. So I did end up finishing a part of this with a walkthrough, which I actually haven't done before with anyone. So this will be kind of fun. But this will just kind of talk about the overall, like how DBSCAN works. So if you remember back, we did k-means, clustering, right? And then we checked out hierarchical clustering, and we saw basically how that kind of works. But one big disadvantage for both of those is that they have to define every point in some kind of group, whether it's its own group or it is, what's it called, like a group of something else. There aren't any no point, like all points have to be in some kind of group. So what's nice about algorithms like DBSCAN, you can actually look for things that are noise and outliers, which is actually really useful at times. And note that I'll kind of use noise and outliers interchangeably. They're technically different things, right? Noise means more in the sense of like, there's just randomness that's like, oh, like it was an accident, or, like accidental, like recording, where an outlier can literally mean like, oh no, this is the true, this is true about like this data point. It's just outside of the rest of the group, or outside of some reasonable expectation of what the data looks like. Okay, so kind of note that there's a little bit of difference between noise and outliers. But I'll use them interchangeably. Okay, so conceptually, how does this work? So I'm going to show a little bit again with that same blog, same author, but it's going to be about DBSCAN. But I'll kind of briefly talk about what it is. Basically, you have all these data points, and you choose a data point. And then at each data point, you just say, okay, you look at some, radius epsilon, and say, are there a minimum number of samples within the epsilon? And if there are, let's say like your minimum number of points are like 4. If there's 4 points within that like circle radius epsilon, then you say, yes, that is a core point. And that point will now be part of a group of some point. If you look at that epsilon and there's nothing minimum sample, but in that epsilon area, there's another core point that exists there, you actually say, oh, good, like that means you should be part of a group, but you'll be something called a border point. And then if there's nothing, if it's not within range of a core point, or there's not enough samples near it, it will basically be determined, oh, you are an outlier. Basically, you are something that's not part of any group, and it'll keep that separate. And basically iterates over all the different points and finds which things are core points, which things are border points, and which things are outliers or noise. Okay. So I think it's best to kind of visually show this versus kind of explaining it through. So again, great blog post here. I just love using this one. But I'll show you first with our basic Gaussian mixture like we had before. And you'll see this like red circles here kind of like in some here. That's because we have 2 hyperparameters we can play around with. One is the epsilon, which is basically how much of a range does each point kind of like look. So this red kind of is showing you a little bit of like how to visualize how big epsilon is. And then min number of points is going to basically how many points needs to be in there before it considers it actually a group. So you can imagine if you have a very small number of min points, basically everything's going to be a group. Versus very large amount of min points, that's going to be very few things are going to be groups because it has to be very densely clustered. Okay, so we'll try to use the default from DBSCAN, which we'll use in scikit-learn, which is 0.05 for epsilon, and I believe min points is 5. So we'll see how this, and we can see there's likely 3 different groups here. So I let this go, and what's happening is going through each data point here, and just looking at those little kind of circles that kind of go out there, is seeing how many points are nearby it, and saying, okay, if there's enough nearby it, it'll mark those as core points or possibly border points. And then what's going to happen is going to go through all of these parts, and then it's going to say, okay, let me go ahead as I get through the border points and see what things, if they're supposed to be a separate group or something else. So you can see by default here, it ends up detecting that most of these, like you can see, actually ends up being 3 groups here. But you can see here it's ending up a group right here, a group right here, a group right here. And all these white points now are determined to be noise. Essentially, it's outside of this group. Now, obviously, it's like, okay, like maybe that's not quite what we wanted here. Maybe we do want to consider all of these points all together. It just all depends on what you want to for your density. So we can adjust from 0.05 and min points of 5. we can do something, the same exact structure, but we'll use epsilon of 1, so a larger radius, and a midpoints of 4. And we'll just change it to 5 just to keep it nice and easy so we don't have to like think about it too hard. So if I increase epsilon to 1.0, will we have bigger groups, smaller groups? What will change just by increasing from 0.5 to 1.0? We got to guess.
I'm guessing that you have less groups because you have a bigger radius.
Good, right? Yeah, that seems reasonable, right? It's considering over a larger radius, more things are in its group. So you can imagine if we make the extreme end, we make it very, very large, right? It'll basically make maybe even possibly one big group because it's so large. Same thing with minimum number of points. If we were to decrease the minimum number of points, we'll have, what's it called? This is my train of thought here. If we decrease it from like, let's say 5, it has to have a minimum of 5 points, and we decrease it all the way to just a minimum of 1 point, it's going to make those things into groups very quickly, right? It's going to say, oh, these aren't outliers. These aren't, noise. This should be part of a group. So you can kind of imagine these two kind of fighting each other, okay? But if we run this now, you can kind of see is that with epsilon 1, we can already see that red is already getting much larger here. We might still have like this point might end up being an outlier. You can kind of see it didn't catch that because it's slightly outside of this epsilon 1. We still have min points of 5. So, if it's not very dense, which I don't think any of these look very less dense, but like you can see like these ones are kind of like on the edge right here. And these could maybe fall with an epsilon, but they're not dense enough to be considered part of the group. So you can see here, this is how we end up getting our different groups. Okay, so it was like, okay, cool, like that worked really well, like in the sense of like adjusting the hyperparameters, making it work, and looks similar to k-means and probably what would be hierarchical clustering, right? We could basically make these 3 different groups, except now we also have this kind of extra noise. Okay, so one that's really useful is something with, let's see here, I'm going to show the pimpled smiley face. So I don't know if you guys can see that too well, but you can see basically it's a smiley face here. So these are kind of like the main groups. You'd expect like 1, 2, 3, maybe 4 groups, maybe more depending on like how we adjust the clustering. But you can see there's some extra data points here that are more like noise. And so we're actually going to see that DBSCAN is going to more or less try to get these into a group, but then try to ignore this noise part. So it all depends on the hyperparameters. That's a big deal. But we'll start off with the default that's on this program. We'll use epsilon 1 and min points of 4. So if I do this now, you'll see here, very quickly identified this as all red. Okay? And then hopefully we'll see most of this, it looks like will end up being blue. Now note that one issue with DBSCAN, which we'll discuss, is that it does have a harder time when the clustering has a different density. So you can imagine like right here is not very dense over here, but it's very dense over here. So what might happen sometimes is that it will actually mark this as a separate group or have kind of a split where basically this group's not going to get connected over here. But you can see here it's basically finding, it looks like in this case, these hyperparameters work out where you end up getting pretty much this one group. And I'll let it kind of finish up, which will basically finish up with this and this over here. So you can see the green right here, and you can see all those little white points are not marked as a group, which makes sense, at least in this scenario where you say, oh yeah, that's kind of more like noise than it is like an actual point. And you can see it did a pretty decent job of what's going through. With k-means, this would basically be nearly impossible to actually make sure it finds this proper points. It just by pure chance, it would maybe find these 3. You might need to modify this essentially to get it to find this outside circle. But you can see it works pretty well. Okay. Any questions on this overall algorithm and how this works?
Is that because the outside circle isn't like one cluster, it just kind of is more like a line of dots?
Yeah, are you saying like why k-means wouldn't perform
yeah,
better
like
on this?
why it would be difficult?
That's right, yeah, because k-means, remember, looks at like closeness. So the problem is that if we're looking at just 2 dimensions, if the centroid's right here, it's only gonna look at the points that are close by here versus looking at the ones that are all connected here. You can technically do something like with the kernel trick where essentially you treat those points that are on the outside and like raise it into, let's say x squared or something like that. And then you can imagine your like centroid being like 3-dimensional. And it's like, oh, it's everything that's close by in this area. But obviously you'd have to kind of like massage that in the right way and everything. So it ends up being a little more complicated.
Okay. And then for the HAC, what would that look like? Or how would that look different? Would it be similar to k-means?
Yeah, so HAC would be kind of an interesting one. It would depend on your linkage, right? It depends if you do like what kind of linkage, but in general, what will happen is that if we do something like Ward, that's going to be really interesting because what's going to happen is that it's going to group, definitely these sides together. Like it'll say like, oh, this is grouped together and probably like this is grouped together. But then to connect these together, it might actually say that these are closer to each other on average than this, like this group right here, if you imagine, and this group right here might be closer in similarity than like this group and like this group over here. So it might actually end up finding that you wouldn't have as nice of a hierarchy. And that kind of makes sense here too, because this data set's not really hierarchical, right? It's more, we can visually see like, oh, this is definitely kind of like it's all together, this one kind of basic shape, but it doesn't really have a hierarchy in the sense that we'd expect this to be similar grouping to this one. So it might not perform very well in this place too.
Okay.
Yeah.
Thank you.
No problem. Cool. Any other questions you guys have between DBSCAN or connecting with the other algorithms we saw for clustering? Okay. Cool. All right, so let's go back to our notebook and just kind of look at what this implementation is. And you can probably see here, I'll just quickly show you the documentation. You can see there's these hyperparameters. The main ones we're going to really think about are epsilon and the minimum number of samples. So epsilon, remember, is going to be basically that distance, kind of like that radius. And note that epsilon also is not just thinking about just in 2D, you can think of it like, if it's 3D or 4D or whatever, however many features you're considering at once. We also have other things like, for example, the metric. As you might be able to guess, this is the distance metric, saying how do you calculate how things are close to each other? So you can imagine adjusting the starting. And there's a few other things we can do too, but I won't go into that. You can check that out if you'd like. But the basic implementation you can already see is basically we import this over from scikit-learn. I'm just adding some extra stuff so we can plot things out later. In this case, I'm having my data set. So I just have this data set. And then you can see here actually creating that DBSCAN is just using the cluster DBSCAN and then just passing the hyperparameters. I believe I think the default is 0.05 for epsilon, and I think it's 5 for min samples. Yeah, so you can see the default is 5. And metric is Euclidean. So that's how we would basically take this guy, we would fit it, and we'd say, cool. And we're all fit. So then we could actually test this out and plot this out and kind of test it out and see like what this looks like and everything. Okay. So really simple. Like I like to say, it's like all these clustering or all the really like machine learning algorithms are relatively simple to implement, right? You can see that basically it's like 2 lines of code to like really like do this whole thing. Most of it's basically importing stuff or like creating the data set. Okay. So some advantages. So what are some clear advantages to DBSCAN? I kind of mentioned it a few times.
I mean, it will not include those outliers that you might.
Right. Yeah, it's going to not include those outliers. We also don't need to specify the number of clusters, right? Which is a big deal. Like with k-means, we have to basically test out k-means multiple times until we find the right fit. We don't really need to specify this. It has a really good flexibility in shapes and sizes, like we saw with that smiley face. It does a really good job of trying to figure out, things that are differently shaped and stuff like this. And again, like Lauren said, deals with noise and outliers, which is a big plus, depending on like what you're trying to look at and stuff. Okay. Some disadvantages is that the border, this is an interesting one. The border can be reached from 2 different clusters. So the thing is that depending on what thing gets started first, these border points might end up actually being taken up by different clusters depending on which one starts first. So that can kind of be an issue by itself. And then also it has a real hard time dealing with clusters with different densities. You can think of something like where it goes really dense, and then kind of less dense in the middle. Is that less dense in the middle supposed to be its own cluster? Is that all noise? It's kind of toss up. And remember, the real reason why it has a trouble with different densities is because you have to define this epsilon in your minimum number of samples, which basically is implying there is some consistent density that you're looking for. Okay. Cool. Any questions on these advantages, disadvantages? Very good.
So we might try, like if we tried an epsilon value and then we're like, oh, I don't know, did that catch them? We would then maybe do several iterations with different epsilon values to see if that makes a difference. That's
right, yeah. And this is actually really true for almost all the algorithms, like the machine learning algorithms we do, all those hyperparameters, right? And remember, the hyperparameters are kind of like the way it learns, right? So you might tweak all the hyperparameters, and we'll actually talk about this today with our pipelines part, but with grid search and such. So you basically, you want to like say, let me try a bunch of different hyperparameters and see how well it performs. We'll actually see that next, so it'll be fun. All right, so I'm gonna move on to a little walkthrough with DBSCAN. And this will let us be able to kind of play around with, you know, kind of testing this out, actually implementing this.